Hello, in this video we are continuing our discussion of section 8.3 on the integral and comparison tests. Specifically in this example we are concentrating on the direct comparison test. So in example 4 we've been asked to determine whether the sum from k equals 2 to infinity of the natural log of k over k cubed converges or diverges. So we are using the direct comparison test, which means that we need to come up with a comparison series bk, and we need to establish some sort of relationship between bk and ak, where ak is how the terms of our original series are written. So this relationship is something like bk is less than or equal to ak, or maybe we'll get that bk is greater than or equal to ak. And then we're going to look at the end behavior of the series bk. And then from there we'll come to a conclusion about our original series AK. But we first need to come up with what the comparison series is. And if you recall from the notes just above this video, there is a rule of thumb. The rule of thumb says to pick the largest variable term in the numerator, the largest variable term in the denominator, and then simplify that ratio. The problem with using that here is the natural log of k is the only term in the numerator, so that must be the largest, and k cubed is the only term in the denominator, so that must be the largest. So if we use that rule of thumb as is, it's just going to give us exactly the same series. So the rule of thumb is a little bit limited in this case, but the notes include, just above this video, some inequalities to remember for the future. Oops, and I apparently can't write that word right now. Inequalities, there we go. So these are inequalities involving the natural log function, and basically this is because the natural log function sort of defies that rule of thumb. So it is good to remember that the natural log of k is greater than 1, and this is true for k bigger than or equal to 3. You can figure this out by thinking about the natural log function, natural log of x, setting it equal to 1. You should get that x is equal to e, which is approximately 2.71. And the natural log of x is an increasing function, so it's going to be bigger than 1 for all x bigger than e. But since we are talking about k being integer values here, we're going to go up to the next largest integer value, so we get this inequality is true for k bigger than or equal to 3. Now we also have an upper bound on the natural log function. So that is that the natural log of k is less than k, and that inequality is true for all positive integer values, so k bigger than or equal to 1. So what this gives is essentially two functions to use instead of the natural log function. Notice for the direct comparison test, we want some sort of inequality relationship between ak and bk. So if we have these relationships here, then we can use that instead of the natural log k in the numerator. But to begin with, we don't know which one of these options is better to use. So let's try using both options and see which one works out better. So I'm going to compare these left and right in our solution. We have option 1, oops, that's a 1, where our comparison series bk is going to be equal to the series 1 over k cubed. So in other words, bk is equal to 1 over k cubed. And this is because of the fact that the natural log of k is bigger than 1. So I've taken this 1 and substituted it in for the natural log of k in the numerator. Option 2, our comparison series bk would be the sum of k over k cubed, which simplifies to 1 over k squared. So in other words, bk is k over k cubed, or 1 over k squared, and this is because of the fact that the natural log of k is less than k. So again, I've taken my k and substituted it in the numerator instead of the natural log function. Okay, so that's our first step. Come up with what the comparison series is. Now we go through the same 3 steps that we saw in the previous example. So step 1 then is going to be to check the end behavior. So the end behavior for the series, and let's just say this starts at k equals 2 to infinity because that's what our original series starts at. This is a p-series. Specifically, p is equal to 3 in this case. 3 is bigger than 1. Since we have a p-value that's larger than 1, this means that it converges. The end behavior for our second option, where we're talking about the series from k equals 2 to infinity of 1 over k squared, so this is the simplified version. This is also a p-series. In this case, p is equal to 2. It's still larger than 1, which means that this comparison series converges also. So that's step 1. Then step 2 is to establish the correct inequality. So for option 1, where we have 1 over k cubed, we use the fact that 1 is less than the natural log of k. So that's going to mean that 1 over k cubed is less than the natural log of k over k cubed. So this is our comparison series, bk. This is our original series, AK. Now we have that our comparison series converges. If the comparison series converges, then what we need is for BK to be larger than AK. Because if you think about it this way, if BK converges, it means that you have a finite sum. So we want to force the original series to have a finite sum as well. So that means that it must be smaller than the comparison. But we do not have that here. So what that means is that this option 1 is inconclusive, unfortunately. So if you had only worked through option 1 and gotten to here at the end, and you would have gotten something inconclusive, then essentially this work that you've done here means nothing because you weren't able to conclude anything. Okay, so just a note then, this solution for option 1 gives nothing useful anyways. So it would get 0 credit essentially. Okay, so be careful. If you get something that's inconclusive, you need to make sure that you consider another case that does end up giving you a result. So let's see if we can get a conclusive result here with option 2. So we had the end behavior and the inequality. Next, again, we're going to use the inequality to remember. So the natural log of k is less than k. This is going to mean that the natural log of k over k cubed is less than k over k cubed, which was simplified to 1 over k squared. So what we have on the right is bk, what we have on the left is ak. So we have that ak is less than bk. And remember, if our comparison series converges, what we want is for ak to be less than bk. and that is what we have here. So this is the right inequality. Since our series BK converges, our comparison series. So then this means that our original series, the sum from k equals 2 to infinity of AK, which is the sum from k equals 2 to infinity of the natural log of k over k cubed, converges by the direct comparison test. Oops, let me get a little bit more room. In case I haven't said this before, now that we have talked about a lot of different series tests, so these tests that you can apply to a series to determine whether it converges or not, since we've talked about a lot of them, if you apply a particular test for a given series, you need to state what test you are applying, okay? And that will be written in the instructions on any graded assignment, but you still need to remember to do it. So you need to apply the test to the series. So that means if we're applying direct comparison, find out a comparison test, find the end behavior, find the inequality, make a conclusion. But you also need to say what test you are applying, unless the problem specifically says which test to apply. So earlier in this section with example 1, it specifically said use the integral test. So there you don't have to say that you are using the integral test because the problem tells you to. This problem just says determine whether the series converges or not. So that means that you do need to state what test that you are applying. Some series that you will see, there is some choice there as to which tests you can apply. And I will talk about a little bit after the next section as to how you should decide between a particular series test for a given series. But I do want to finish talking about all of the different tests before I talk about how you choose which test. But anyways, what I was saying here for this example is make sure that you write which test you're using. In this case, we are using the direct comparison test, and we have concluded that our series converges.